Swayam Prabha. Digital India. Educated India.
Previous class, I spoke about different approaches for modeling single phase turbulent flows. Broadly, we have three different kind of modeling approaches. One is direct numerical simulation, then Reynolds average Navier-Stokes based modeling, and then large eddy simulation. And I have already discussed the advantages and limitations of direct numerical simulation approach, where basically you don't rely on any models, rather you try to resolve the turbulence at all scales. So you resolve the turbulence energy spectrum fully, but the main issue in this case is the computational time. Next, we have Reynolds averaged Navier-Stokes based modeling. So in this approach, what we do is we decompose the instantaneous velocity to mean and fluctuations. The popular approach. Sometimes people assume that this is the only way to model turbulence. In fact, this is considered as the only equations for turbulence, which is not true. This is only one way of modeling the turbulent flows. So if we introduce this to our continuity equation and momentum equation, then we can express those equations in terms of the mean parameter. So for example, the Navier-Stokes equation can be written as shown here. So you see that this equation is quite similar to the Navier-Stokes equation. Instead of instantaneous velocity, here we have mean velocity components, but this gives rise to, or this kind of decomposition gives rise to this extra term, which contains the correlation between the different velocity components. We have already discussed what is meant by correlation between two quantities. So this basically represents the divergence of Reynolds stresses, where Reynolds stress is given by this. So this in Rans based modeling, this term represents the effect of turbulence on the mean flow. So how the mean flow would change due to turbulence. So now this brings us to the Reynolds stress tensor, which is shown here. So you see that there are 9 components, but they are the non-diagonal components are symmetric. So eventually here you have 6 components. So this is the Reynolds stress tensor. Now in the diagonal we have the so-called normal stresses, which basically represents the turbulent kinetic energy, while the off-diagonal terms refer to the turbulent shear stress. Now, how would this stress tensor change or it will be modified if we have isotropic turbulence? So we know that for isotropic turbulence, the velocity fluctuations in the 3 directions are statistically equivalent. Okay. So now we can represent the diagonal terms in terms of turbulent kinetic energy. So here, if all 3 are same, then this can be written as individual components. We can write this in terms of the turbulent kinetic energy. But now what you see here, that the turbulent shear stress terms are now 0. Why? What makes the correlation between different velocity components 0 if we have isotropic turbulence? So, as I mentioned earlier, so if we have some finite correlation, what does that mean? Now, let us say you have positive correlation. So, this means that if U component increases, then V component also increases, and vice versa. If U component reduces, V component also reduces. So, this means that they are correlated to each other. However, if my flow is isotropic, I can rotate the coordinate axis and still get the same result. I should get the same result. So, now imagine I rotate this by 90 degree in the anti-clockwise direction, such that now I have this as U and this as V. And if I calculate now the Reynolds stress term U dash V dash, then that should be equal to what I have got here. Okay. Now, that can be equal only, it can be shown that that can be equal only when the value is 0. So, that the condition that this correlation is independent of the direction can be met only when the correlation is 0. So, in other words, if you have the correlation like this. So, in this case, if you calculate U dash V dash, what does this mean? This means that at each point you calculate this product U dash V dash and then sum them up, take the average, then it will be 0. Now, if I rotate the coordinate to any direction, still I will get the same answer, but that won't be true if you have some finite correlation. So, this is the reason why these terms vanish if we have isotropic turbulence. But now the question is, how do we model this? Now the question is, why should we model? So, now if you see the unknown, how many unknowns are there in this equation? You are solving for 3 mean components. So, you have U mean, V mean, W mean. But in addition, you have these 6 turbulent stress terms, and we do not have any equations for them. So, eventually you have 3 equations, say continuity, 4 equations, but 6 unknowns. So, that is why we have a closure problem. Okay. So, this is the reason why we have to, if we want to solve this, then we have to express the Reynolds stress somehow in terms of these quantities, then only you can solve it. And that is what is meant by modeling in the RANS, modeling in RANS based approach. Okay, so there are different approaches to modeling, to do turbulence modeling in the framework of RANS. The first one is eddy viscosity model. So, what is eddy viscosity model is that in this case we assume that the Reynolds stress behaves as shear stress. So, like we have simple shear, and here we have the dynamic viscosity. Same way we have, according to this model, which is based on basically Bosnick's hypothesis, we have something called eddy viscosity. So, this is not a physically realistic parameter. Okay. This is used to model turbulence in RANS based approach. So, we can express the Reynolds stress in this form. So, here you see that we have this is the mean strain rate and this is the eddy viscosity, and we have the turbulent kinetic energy terms along with the Kronecker delta function. So, this means that this term survives only for the diagonal terms. Now, basically different models differ in how we compute these two terms. So, we wanted to eliminate the or express the Reynolds stress terms in terms of mean components. But now instead of that, we have two, through this type of model, we have now two unknowns. So, how do we model these two? So, then we have zero equation model, which is basically an algebraic model. For example, mixing length model by Pruntil. So, you would have come across when you studied turbulence. So, in this model, we assume that the Reynolds stress here is equal to the ED viscosity times the gradient of velocity. Now, the ED viscosity itself is equal to mixing length square times the gradient of velocity, where the mixing length is modeled as ky, where basically the mixing length is proportional to the distance. Okay. And this is how you model the stress term. Now, obviously, this approach is very simple, as we do not have any further equations to solve. This is a simple closure, you can say, and it works well for canonical turbulent shear flows, for example, boundary layers or pipe flows. However, there are limitations too. So, basically it cannot capture the flow separation or recirculation, as there is no turbulence transport included here. It is not valid very close to the wall or in complex 3D flows, and it assumes local equilibrium between production and dissipation of turbulence. So, basically this assumes that your net rate of transport of turbulent kinetic energy is 0. Basically, if you assume that there is no transport of turbulent kinetic energy, then there is computation between production and dissipation. And according to this model, whatever is produced is dissipated, and there is negligible transport. That is the reason why the local transport term is 0. And this is the reason why it is unable to handle situations like flow separation or recirculation. For example, flow separation past a bluff body, it will not be able to handle that, or in other words, the accuracy will be low. So, similarly, in all other approaches, there are pros and cons. This is only one example. The other type of modeling approach is one equation model, where we solve the transport equation for the turbulent kinetic energy and use a length scale to compute nu t. So, remember that we have now two unknowns, turbulent kinetic energy and the ED viscosity. So, now how do we bring up different approaches to solve them? So, this is one equation model, because you are using only one equation for turbulent kinetic energy. Then we have also two equation model, where we solve the transport equations for two turbulence quantity to get both velocity scale and length scale. So, here we have K epsilon models. You would have come across this earlier, at least you would have heard of this in the context of turbulence modeling. So, there are different types of K epsilon models also, based on how do we relate them to find the ED viscosity. For example, this is the example for the standard K epsilon model. So, here we solve the turbulent kinetic energy transport equation, which is this one, we had already discussed this, and we have another equation for the dissipation rate also. So, why dissipation rate is required? Because we use that to calculate the ED viscosity. So, now here we will have the turbulent kinetic energy and the ED viscosity. So, similarly, we have other K epsilon models. we can also have K omega model, where omega actually refers to specific dissipation rate. We can have K omega model or SST K omega model. All these models try to use different approaches to find the eddy viscosity and the turbulent kinetic energy. So now the advantage of these models, one equation and two equation models, are they are simple, robust, and they are widely used. The main advantage is the computational time here with some level of accuracy. And the limitations are basically it assumes isotropic turbulence. You have poor predictions in swirling, separated, and highly anisotropic flow. So the higher is the anisotropy, more is the inaccuracy. Then we have this refers to another set of modeling approach. The first one was based on eddy viscosity, but here this is Reynolds stress models. So in this case, instead of using eddy viscosity, we directly solve the transport equations for the Reynolds stress components. So here we have the equations for the Reynolds stress component itself. So here you can see, for example, we have the equation for the Reynolds stress term. We have production, dissipation, diffusion, and pressure strain correlation terms. And in addition, here we have the dissipation, so we have to solve the equation for dissipation as well. So this approach obviously works better compared to the eddy viscosity model, because here you are solving the transport equations for the stress tensor component itself. But here you have these additional equations coming into picture, and that is why it is computationally expensive, and also convergence might be an issue. Then the third approach for turbulence modeling is large eddy simulation. Now, we know that in case of direct numerical simulation, we resolve all turbulent scales, but it is extremely expensive. In case of RANs, it is blind to the turbulent eddies. Basically, it considers turbulence as U dash only, and you are modeling directly for this. So basically, you model for all turbulent eddies, because it assumes that you have only U dash that represents turbulence. However, from Kolmogorov hypothesis, we know that that is not the case. Here itself, when we say U dash, it contains the large scale eddies, the intermediate eddies, and the small scale eddies also. So RANS is blind to this this division. So but in the case of LES, we resolve large energy containing eddies and model only the small and dissipative scales. So if I sketch the turbulence power spectrum, so in DNS you resolve everything. In RANS, you don't resolve the eddies, you directly model it. But please remember that you model the turbulent stress terms, but in RANS what you get is the mean quantities only. We don't have information on the turbulence quantity. Yes, according to the model that you use, you have these terms. You can calculate the standard deviation of the fluctuations. You can calculate the turbulent kinetic energy, dissipation rate, but these are all models. But you have no information on the instantaneous flow field. Now, why this is important? Later, when we will consider multiphase flows. So you have now, imagine particles in your flow. So you have, let's say, a jet, a turbulent jet having particles. So now, if you solve the Ran's equation, you get the mean flow only. You have information for the mean flow only. So now, if you want to model the particles, you can consider their encounter with mean flow only, which is actually a hypothetical situation. For modeling purpose, we can do this, but when you have a flow is a flow. That itself does not have mean or fluctuating components in reality, right? What you have is instantaneous velocity, and particles interact with that. So all these factors are important when we consider the multiphase flows. Okay. So in case of LES, what we resolve is basically the energy containing ED. So you know that you have, so this is the large ED, this is the intermediate, and this is the small. So in case of LES, we resolve, let's say, up to here. You resolve means your grid size is smaller than this length scale, and then you assume that this part is anyway universal. The flow boundaries won't affect this. What will affect is only Reynolds number. So based on this assumption, you assume that, okay, this is prescribed, so I don't have to bother about it, and you prescribe this. So you through some model, and what you resolve is only this part, mainly the large EDs. So that is why its name is large ED simulation. You resolve the large EDs. And LES is often called a scale resolving simulation. So what do we do in this approach is that we again do a decomposition. So instantaneous velocity is equal to this u bar plus u dash. However, please remember that these are not same as what you do in case of RANs. You can think in case of RANs, you have, let's say, you take one single point in the flow and you have the flow velocity fluctuations, or these are the instantaneous velocity. This is at one point, and then you consider the mean, you consider the fluctuations. But in case of LES, you do spatial filtering. So now imagine you divide this into different regions or grids. So now I consider all points here and I do averaging then. I hope it is clear. So this is spatial averaging, and this u bar refers to that, and that is why this is a function of time also. Okay. Plus you have this fluctuation, but it does not correspond to fluctuations how you define in case of RANs. Why you have fluctuation? You will have fluctuation because the velocity at all these points are not same. So now these are, you need to basically model this part. So if we now introduce this to continuity and momentum equation, you get equation like this. This is very similar to the RANs equation again, but here also you have a term similar to RANs, but these are known as subgrid scale fluctuations, okay, which is given by this. So instead of Reynolds stress tensor, we call it subgrid scale or SGS stress tensor. So now similar to how we did modeling for Reynolds stress in case of RANS based approach, we have to model the SGS stress tensor. So, this is about the LES model. So, there are various models available. One popular one is Smagronski or dynamic Smagronski model. There are other models also available. We are not going detail into it. Now, what are the key features of LES? The key features are basically it provides time resolved flow field. So, this is unlike RANS. We have unsteady 3D turbulence information in case of LES. In terms of accuracy, this is much higher than RANS, especially for unsteady, separated and vortex dominated flows. But its computational cost is also much higher than RANS, but still far less than DNS. So, you can imagine LES in between RANS and DNS. Now, accordingly the grid size, if you see the grid size is much larger than Kolmogorov scale, but it has to be much smaller than the large ED scales because you are resolving the large EDs. If the grid size is coarse, if you move in this direction, then it will resolve mostly energy containing scales and models most of the inertial range, but it will behave more or less like a time dependent RANS. So, if your grid size is larger and larger, you are going towards unsteady RANS. Similarly, if your grid size is smaller and smaller, then you approach DNS. Then the benefit of LES is gone. So, if you make the grid size too small, then you are approaching DNS. So, the computational cost is anyway again high. So, that is why the accuracy of LES strongly depends on the resolution of the grid. So, the grid has to be optimally resolved. Okay. Okay. So, now with this basics that you have gained so far on carrier phase equations along with the source terms and then the basics of turbulence and turbulence modeling, we are now ready to discuss particle turbulence interaction. Okay. So, now what is meant by particle turbulence interaction, or the question here is how do particles interact with turbulence, or how this situation is different compared to what we discussed earlier, that is interaction of particles with laminar flows. So, for this we have to look at this picture. So, now we have particles of various sizes and now we have carrier phase which is turbulent. So, that contains wide range of EDs of different length and time scales. So, the question is how do we now predict particle behavior? So, for that, so if the interest is on to study how a particle would behave, what is the parameter that you want to calculate? What is the non-dimensional parameter which is of importance? That is Stokes number. So, what is Stokes number? The ratio of the particle response time to time scale of the flow. So, now if you consider polydispersed particles which has a wide range of sizes, then the particle relaxation time is different for different particles. So, if you consider the laminar case, so in that case we used to have a single or discrete time scales. So, now if you consider a particle of a given size, its behavior is same, but now in case of turbulent flows, you have, the question is which flow time scale should be used? What should be this flow time scale? Why? Because the time scale of the eddies depends on the eddy size. The time scale of the large eddies and small eddies are not same. So now we can't get away by saying that there exists only one discrete time scale of the flow. So we have time scale which varies with eddy size. So this means that we have wide range of Stokes number. Now what does that mean? Even if you consider particle of a given size, the Stokes number is different based on if it is interacting with a large eddy or a small eddy. Okay. So it may behave like a tracer particle for a large eddy. For example, if you calculate Stokes number for a large eddy, so we know how to calculate now the large eddy time scale. How do you calculate? First you need to estimate the large eddy size and then the velocity fluctuation. So this is basically the large eddy time scale. So if you calculate Stokes number based on that, you may see that Stokes number is much smaller than 1, which means that the particles would follow the large scale eddies. But now if you calculate Stokes number based on Kolmogorov scale, so how do you calculate the Kolmogorov time scale? So this is basically, we know that it's a function of dissipation rate and the kinematic viscosity. Okay. So now if you calculate this, you may find that in this case the Stokes number is much greater than 1. So this means that the particle, when it is interacting with small scale eddies, it is behaving like a ballistic particle. That is, as far as small scale eddies are concerned, the particle would just pass through the eddy without interacting it. This is just one scenario. It may be possible that all particles are behaving like a flow tracer. When that is possible? If the Stokes number based on the small scale eddy itself is very small, then obviously it will be much smaller when we have large scale eddies. Okay. So those particles actually can be categorized as flow tracers. So when we say flow tracers, these are those particles which track all turbulent eddies. Okay. On the other hand, if a particle Stokes number, if the Stokes number of a particle based on large scale eddy itself is much greater than 1, let's say it is 100, then obviously it won't respond to small scale eddies also. But this brings us the complexity, because you don't have particles of a given size. You have polydispersed particles. So now the behavior of each particle is different to different eddies, and now if you change the particle size, now because of size itself, now the behavior is different. So the question is, if I now put bunch of particles of different size in a turbulent flow, how would they behave? So this means that you have to track individual particles to see their behavior. Okay. And that is basically the essence of the particle turbulence interaction. So now when we say particle turbulence interaction, there are two aspects to it. One is how turbulence influences particles. So imagine you put some particles in this room and there is no flow, or you have a laminar flow, and suddenly now you make it turbulent. Now how the particles would be dispersed, which means that how the spatial distribution of particles will be affected. So that is how turbulence influences particle behavior. Or if you want to make it more complex, you can say that, okay, now how turbulence influences, let's say, droplet evaporation rate. If you have evaporating particles, how turbulence would influence the mass transfer. And should that depend on the size? So when we say the dispersion of particles, you need to consider only the momentum equation, momentum coupling. But if you say evaporation, then you have to consider mass effect of turbulence on mass transfer. Similarly, effect of turbulence on heat transfer. So if I have particles of different size which are at initially, let's say at same temperature, but higher than the carrier phase flow temperature, then once the interaction starts, particles of which size would respond better? Okay, so that is, these are all related to influence of turbulence on particles. But the story does not stop there. There is a back effect. How do now particles influence turbulence? Because we know that even if we have absence of any mass and heat transfer, the momentum coupling is always there. So the particles can influence the turbulence. How? They can modify the turbulence power spectrum itself. So now let's say you have a turbulent flow and this is your power spectrum. Okay. Now if you put particles, what would happen to the eddies? What would happen to, for example, Kolmogorov eddy? Will it be larger or smaller? What would happen to large scale eddies? So can I expect some difference? For example, can it change like this? That is possible. So we know that if the particle loading goes beyond some limit, then we have two-way coupling. That means the particles would influence the carrier phase. But now what is interesting in case of turbulence, how would that affect the eddies at different scales? So it may happen that the large scale, in case of large scale eddies, the turbulent kinetic energy, let's say, goes down, but small scale eddies, it goes up. So you may see overall no change, but at individual scale level, there can be a change. That is also possible. So that is why this is more complex. So we'll continue this in the next class.